Hello, everybody. Welcome back to Thermodynamics. We'll get started, but the first thing that I wanted to talk about today was just to remind everyone that we have an exam coming up. So the exam will be on Tuesday. Will run from 3 p.m. So the materials, both the multiple choice, which will be available as a quiz on my courses, and the long answer problems, which will be available as a document on my courses. You'll be able to access those from 3 p.m. to 7 p.m. As we discussed last class, there's no time limit outside of that time range. So it's not like you can only access it for 2 hours of that block. So you'll have access to the exam for that whole time. And from 5:15 to 7 p.m., I'll run a Zoom meeting in this same meeting room if you have any questions about the exam. So that time frame from 3 to 7 is sort of the standard time frame, and if you have accommodations that have been approved by the university, then we will honor any extended time associated with that. Does anyone have questions about the exam? Okay, well, then we will move forward. So today there's sort of two topics that we're going to cover. So first, I'll do a review of basically what's on this first midterm. So how do we deal with closed systems? And then the back half of the class will be an example problem, so a first law problem, but a problem where the working fluid is an ideal gas, in this case air, and we'll go over how to solve the problem by assuming constant specific heats and by assuming variable specific heats. So when we look at this first midterm, we've talked about what to do with closed systems. So I think any of these topics are sort of fair game for either the multiple choice or the long answer problems. So remember in the sort of pre-material, we talked about, different units and definitions, mass versus weight, all that kind of stuff, pressure, work, power, modes of heat transfer. How do we deal with the first law? What is the first law? What does that expression look like as, for closed systems? How do we deal with specific heats for solids and liquids? What assumptions do we have to make for ideal gases in order to use specific heats? Once we're trying to use the first law and we get down to this place where we're trying to find internal energies or specific internal energies, how do I fix those states? How do I find those values for little u? If it's water, I got to say, is it a subcooled liquid or a two-phase mixture or a superheated vapor? If it's an ideal gas, I have to ask myself, am I assuming constant specific heat or variable specific heat? So, when we're doing this, we'll say, so what's the fluid? It's always a bit of a two-part question, right? We want to know what's inside of our system. So what's the fluid that we're talking about? And then if the fluid is water, we ask, what phase is that water? Is it subcooled, two-phase, or superheated vapor? So those are the two parts if it's water. The two parts if it's an ideal gas. So first is what's the fluid? It's an ideal gas. And the second part of that question is, are we going to use constant specific heats? So we can say that delta U is CV times delta T. Or are we going to say that it's variable specific heats, where for air we would use table A22? And we'll go over both of those methods today. So just going through kind of week by week, week one, or maybe it's week zero, the week before we got here, we had lots of different definitions, right? So there was kind of a lot of things that we went over that were covered in that first quiz. So you'll need to know those definitions, units and properties, appropriate units in SI and imperial styles. And the definitions that we need to know are not limited to just the ones that are in that week one slide. So we've talked about things like polytropic processes, where you have PV to some exponent is equal to a constant, right? We've talked about adiabatic processes, where Q is equal to 0. So we have some terms that we need to know the definition of that weren't necessarily covered in that first sort of pre-week of learning. We did talk about mass versus weight in that, before we got into class. right? So here, this is kind of a manometer type problem. You could see something like this on the exam where we see that the difference in this height is related to the weight of this fluid that's sort of this fluid difference, right? So if we were talking about this pressure difference in the metric system, it's a nice equation, right? We get that the pressure difference here between the top and point B is equal to the density times gravitational acceleration G times L, right? L is this height, which is the volume divided by the area. That's where that came from, right? So it's rho GL or rho GH, right? The problem is that when we talked about mass versus weight, that everything gets a little trickier in imperial units. So so the long answer problems, there's two of them. You should expect for all the exams that we do, one of those problems will be in SI units, and one of those problems will be in imperial units, right? So whenever we're dealing with not the metric system, right, we have all of these extra little quirks. And one of them is that if we were trying to calculate pressure like this, then we don't use the equation rho GH, right? Instead, we use this equation rho G divided by GC times H, or L in this case, right? So it's a little weird, and it comes from this idea that, the imperial system is older, so, you have pounds mass and pounds force, and they both seem like they're in the same unit, but they're measuring different things. So, we know that 1 pound mass has a weight of 1 pound force if you're here on Earth, right? So if the relative gravity is 1, right? So GC is like the gravitational acceleration on Earth, although the units are a little bit funny to make these equations work. So G over GC is the actual gravitational acceleration divided by this kind of standardization, this gravitational acceleration on Earth, right? So we get these weird things, right? Our spidey sense should always start tingling, or maybe we feel this sort of disturbance in the force anytime we're dealing with imperial units, right? So it gets a little trickier, right? But either way, we're going to use the same base equation when we're talking about processes in thermodynamic class, right? Because really, like we said, this class is about conservation of energy. So we're always trying to conserve energy, and so far we know how to deal with closed systems. So conservation of energy, or the first law of thermodynamics for closed systems, is that the change in energy in my system is equal to the heat in minus the work out, right? So we know how to find work because we have this PV diagram, right? So work is the integral of P dV, and we showed why that is, right? We showed how that gives us, a force times the distance, which is work, right? So we know that work, the equation that we will use for work in this class for closed systems is work is the integral of P dV from the volume at state 1 to the volume at state 2. If we have a polytropic process where we can define PV to the power of n is equal to some constant, then what we can do is we take this part of the equation, right? And we divide both sides by V to the power of n, and now we get pressure as a function of volume. We put that into our integral, and now we do the integration, and we can get one of several different forms of this equation. So if the volume is constant, then we get that the work is equal to 0. If the pressure is constant, we get P times delta V. If PV is constant, then when we do this integration, we get 1 over V, so we have to start using the natural log, right? Or if we get V is not equal to, or N is not equal to 1, we have this kind of general form that we see here, right? So we have different equations for work, but to me, it just depends how you like to study. For me, I'm not great at memorizing things. I'm better at understanding systems. So here, I like to just know that I can take the integral, and then when I have my PV relationship, I can get to this equation instead of memorizing which equation goes with which case. So that's how we deal with work. The left-hand side of the equation we'll deal with by first, so to find the change in the energy, first thing we'll usually do is we'll remember that this change in energy is equal to the change in all kinds of different energies. But in this class, it's typically the internal energy that we care about. So we'll do things like neglect kinetic energy and potential energy. So when you write down your assumptions on your exam, you need to tell me what you're doing, right? If you just write down this equation, then you haven't demonstrated your understanding of the problem because you haven't told me why you got to delta U. So tell me what assumptions that you're making. We see that work is the integral of PDV, and then we can find the change in the specific internal energy and multiply it by the mass, right? And then typically, because you're not in third year yet, right? You haven't taken heat transfer, so you don't know how to find Q sort of from first principles. So instead, we'll typically use the first law to try to find the heat transferred in these processes. But to do that, we need to find the work and we need to find the change in internal energy. We've learned now several different strategies for finding delta little u, the change in the specific internal energy. And for both ideal gases and sometimes for solids or incompressible liquids, we can either use tables or we can use CV times delta T. I like to remember that CV goes with delta U because V and U look kind of similar, at least if I squint, right? So I have to ask myself, what's the fluid? What's inside my system? And if the answer is water or maybe some kind of refrigerant, so you may or may not know this, but in your air conditioner, in your refrigerator, what happens is the coolant that's in there, the refrigerant, is going through this process where it's constantly evaporating and then condensing, and it kind of shuttles back and forth, right? So it's also going across the vapor dome, right? So we do this with water as we boil and condense, but we also do this in air conditioning or sort of temperature control type systems. So if we were talking about water, the second part of that question is, okay, what's the fluid? Oh, it's water. Oh, if it's water, now what phase am I in? Am I a subcooled liquid, right? This is like water coming out of my tap. Am I a superheated vapor, which is steam? Or am I some mixture of liquid water and water vapor that both exist at the right conditions for phase change, right? That's saturated water vapor or water sort of liquid vapor mixture, right? This two-phase envelope, right? Or the vapor dome. For ideal gases, we can make the assumption that it's an ideal gas we found if this compressibility factor, or Z, is equal to 1. So we talked a little bit fundamentally about what happens and how we get this graph. That's a little bit beyond the scope. You'll need to know kind of definitions about these things, but I'll never ask you to find the value of Z for something. But it's important to know when this compressibility factor, when it's going to be approximately 1, right? So when is it reasonable to say something is an ideal gas? And the answer is when the temperature is much higher than the critical temperature. That's the temperature that's right at the peak of the vapor dome, right? Or if the reduced pressure or the pressure is much less than the critical pressure. Because here we see when the reduced pressure gets low, all of these values converge to 1. Or when TR is high, then this curve flattens out. So if we have one of those two things, it's probably fairly reasonable to say that we have an ideal gas. So if we have an ideal gas law, in this class, we'll use, we talked about this a little bit, right? So because we're engineers and we're typically talking about fairly large amounts of mass, we'll talk about mass typically in terms of pounds mass or kilograms instead of moles. So we will be using not the universal gas constant, R bar, but the specific gas constant, which will be different for every gas. And we would get that by taking the universal gas constant divided by the molar mass of whatever gas we're talking about. So we can use the ideal gas law in several different forms, right? So we have, this is maybe the one that we're most familiar with, right? So this is pressure times volume is equal to mass times the specific gas constant times temperature. But if I divided both sides of this equation by the mass, then I would also see that the pressure times the specific volume is equal to the specific gas constant times temperature, right? So that's the ideal gas law too. And that's good if I'm trying to find, so let's say I have a particular state and I know the pressure and the specific volume, but I want to find the temperature. Then this equation is the equation that I want to use. But sometimes I'll have some process for an ideal gas. And if I'm going between states, I might want to use a case like this. So what's cool, right? If we have an ideal gas and it's not undergoing some kind of chemical change, that means that the gas is not changing, which means that the specific gas constant R is also constant. And if that's the case, then P1 times the specific volume of 1 divided by T1 is equal to R, right? I get that from this equation here. But that's also true for state 2. So maybe I don't even care what the specific gas constant is, but from this equation, I can see that P1 V1 over T1 is equal to P2 V2 over T2. Now, because we're talking about closed systems, this is also going to be true not just for the specific volumes, but for the volumes as well. So here, if I multiplied all 3 of these terms by the mass, then these specific volumes would turn into volumes, and my center term here would become mass times the specific gas constant. But the mass is constant because it's a closed system. The specific gas constant is constant, provided that we're not undergoing some kind of chemical reaction and the gas is changing. So then the pressure times the volume over the temperature is also constant between my 2 states. So if you're trying to find some information at one particular state and you have some information, you might want to use this equation or this equation. But if you're moving between states, then you might want to use this equation or this equation. So there's different ways that we can use the ideal gas law. One of the other things that's nice about the ideal gas law and for incompressible fluids or solids is we can use this definition for specific heats. That the specific heat under constant volume, you can see that I get this same notification every day. I don't know why. I don't. Maybe there's some way I can change the timing that happens so you don't get to see that my things from work are not up to date every single time, right? So here, our specific heat at constant volume is equal to the derivative of U with respect to temperature, and Cp is the same thing, the derivative of specific enthalpy with respect to temperature. So this is why, if we assume that these specific heats are constant, which is not unreasonable for ideal gases, incompressible liquids, and solids, then we can say that delta U is equal to CV times delta T, or that delta H, if we ever need to find it, which will be mostly after this exam when we start to look at open systems, but delta H would be Cp times delta T. For ideal gases, it's important to remember that Cv goes with U and Cp goes with H. For solids and liquids, Cv and Cp are the same. So it doesn't really matter which one you use. And in some tables, they won't even have Cv and Cp. They'll just have C as specific heat. So if we're dealing with ideal gases and we assume that the specific heats are not constant. So constant specific heat's a reasonable assumption, particularly when your temperature difference between your 2 states is not exceptionally high, but the assumption gets worse the bigger that delta T gets. So in some cases, you may want better accuracy, and maybe you want variable specific heats for your ideal gases, in which case for air, you would have to use table A22. And we'll do an example at the end of this class showing how to find delta U with constant specific heats and how to find U with variable specific heats when we're dealing with ideal gases. So I hope you don't get to this point, but it's certainly possible that when we have this first exam, you're looking at the question and you feel lost, right? So this is kind of like, what do you do if you don't know what to do, right? So the first thing that I think is useful is it's nice to be able to draw things like PV and TV diagrams. I think there's 2 reasons why this is good. So if you can draw a PV diagram, then you remember as you go between different states that the work is the integral of PdV, and that's going to be the area under the curve for your process on a PV diagram. TV diagrams are also nice. Both of these curves, being able to draw both of these curves is useful if you're dealing with, say, liquids, right? So if you're dealing with water and it's going through some kind of phase change, being able to draw these graphs will help you get a first approximation or a guess about what phase your water is in, whether it's liquid water or two-phase mixture or superheated vapor. I think it's always nice to draw a state table because it helps us account for the information. It's kind of a one-stop shop for where all your information is, but it's also a nice way to see where you might be able to fix a state. So if you have a state table and on a particular row you have two independent intensive properties, then you'll know that you have a shot at fixing that state if you can figure out where to look up the information. Sometimes it's useful to draw a process table. So as you go between states 1 to 2, there'll be a certain amount of work and a certain amount of heat transfer. Again, that's for accounting and maybe makes it easier for you to think and process how to move your way through the problem. I think sometimes when you get, maybe you feel this way, maybe you don't, but I think, when you get a test, the hardest part about a problem is when you first read it, right? And you have those first couple minutes where it's like, man, I don't know what I'm supposed to do. And I think one of the things that we know about engineering and about, maybe life in general is having a systematic approach will help you get through those first couple minutes, right? So if you can say, okay, I need the first law, I got to ask myself, what's the fluid? And if it's water, what's the phase? And if it's air, is it constant or variable specific heat? I got this state table, I can start to write things down. Sometimes you just get a little bit of inertia and then, that'll let your instincts kind of kick in a little bit, right? So now that you have this state table, you can have your symbolic solution for the first law. You can see where you can start to fix states, right? And then you can, in the process table, if you want, you can start to say, okay, how am I going to find work, right? So you want to say, okay, there's this process information. Maybe the problem tells me, oh, there's some relationship, PV to the n is constant. And then you kind of remember, okay, I'm going to write that down. Oh, now I got to take the integral of PdV. Okay, how do I do that? What's the answer going to look like? Right? And then you can start to use the first law. You make some assumptions. You say, now I need to change in internal energy. I'm going to find work. And now with those two pieces of information, you can find the heat transfer. Right? Now, basically, if you have a series of processes, then what you do is you just kind of like, you draw a loop in here and you do, steps 4 to 6 until your state table is completed. Right? Again, I guess the caveat that's maybe not here is that it's nice, I think, to start with the first law stuff so that you can see what are the variables you need to fill in on your state table so that you don't get to a point where, you're just filling in the state table and taking up time with variables that you don't necessarily need. Right? So I think, again, if you're going through this, another way to look at it is you can ask these kind of questions, right? So what's my system and what's my surroundings? Is my system open or closed? We only know how to do closed systems, right? So if it's a closed system, that means we use the closed version of the first law of thermodynamics, right? This is thermodynamics class. So again, if you don't know what to do, write out the first law because there's a good chance that you need to do the first law for whatever problem I'm going to ask you. Right? Now that you've written out your first law, you make some assumptions. And those assumptions at least will get you from delta E to delta U, right? So you got to remember what those assumptions are. Use some process information. So try to get pressure as a function of volume, then integrate to find work. So here, you could look at this, right? Your delta U became M times delta little u, Q, and work became the integral of PdV. Now you ask, what's my fluid, right? And if my fluid is water, then I got to say, okay, is it a subcooled liquid, right? Is it liquid water? Then delta U is CV delta T, or just U by itself is going to be approximately equal to UF at the same temperature. If it's a two-phase mixture, were you given quality? Or maybe were you given specific volume that you could use to find quality or something like that? If it's superheated vapor, then you try to go through the tables and find the information that you need to do some kind of linear interpolation. If it's an ideal gas, You have to say, is it constant specific heat? And if it's constant specific heat, then you can use delta U is equal to CV times delta T. Or is it variable specific heat where you'd look it up on A22? For long answer problems, and probably for multiple choice too, I will specify whether or not you should use a constant specific heat or variable specific heat analysis. Now, I think it's best for your grade if you do it the way that I ask you to do it. But if for whatever reason you don't remember how to do it that way, the next best thing is to do it the other way, right? But if you kind of remember this process, then you should not ever turn in something to me that's blank, right? Because my heart, it breaks a little bit every time I see a blank exam paper because, I think the whole purpose of an exam is to give you the opportunity to demonstrate your understanding of the material that we've covered, right? And, even if it's just a symbolic solution or kind of a process flow like this, you're showing me something about what you understand, right? There's nothing that I can do to help you if you give me a blank piece of paper, right? And then after we do this, after we find the work and we find delta U, then we put that information together and we find Q. Finally, what we do at the end is we look at all of the things that we calculated. We say, do those things make sense, right? I know that heat in is positive and work in is negative. So if I look at the signs of my answers, do they make sense with my sort of intuitive understanding of the process, or sometimes even the verbal description of the process? If it says that heat is added to my system, I'm really expecting to get a positive value of Q. And if I don't, even if it's the end of the exam and you don't have time to go back and fix it, tell me. If you think something, you do your problem and you feel like you're getting an answer that doesn't sort of line up with your intuition of the problem, tell me. Write it down. Say, I got a value for Q here and it's nice. It's in the right units, but I think the sign is wrong. You write that down because then I can see, Michael got the problem wrong. He didn't get the right answer, but he noticed that his answer was wrong. This happened to me once in my heat transfer class, right? It was a brutal class, right? So the professor, he was almost retired and he'd been there forever. And on campus, he was sort of known for having the hardest class. And he gave us no information basically on the problem and said, model this soldering iron and tell me how long it takes to heat up. The answer that I got was that it took like 3 weeks for the soldering iron to heat up. I knew that was wrong, right? So that product would never sell one single unit, right? Because no one is going to wait 3 weeks for their soldering iron to heat up. So, but my process was okay. Just I probably made some kind of unit conversion error, or I did something to get this ridiculously large number that made no sense. But I told the professor that I knew that the number didn't make any sense, and I think that showed some understanding on my part, even though I didn't get the answer right. So that was, I have a problem now, right? But before that, is there anything kind of conceptually, any questions about sort of the content that's going to be on the exam? You're welcome to write questions in the chat or to unmute yourself. Okay, so the last thing that I wanted to do, right? So last class we went over a nice example, but the example was for a system that had water in it, right? Water vapor, some transition of water in there, right? But on the exam, you might see, we talked about this kind of decision matrix, this flow chart, and when we ask what's the fluid, sometimes the answer is going to be water, but sometimes the answer is going to be it's an ideal gas. So I thought it was valuable if we went through a problem where we dealt with an ideal gas. This is also a problem in imperial units, just so we remember that on the exam, you will see both, right? Maybe it's the Canadian me, but by the end of this class, I'm sure you will, like me, have a much stronger preference for the metric system than for this imperial system, right? And we'll blame the British, right? Right, because it's the imperial system, right? So here, we're going from state one, where we know the pressure is 80 pounds per square inch, the volume is 0.1 cubic feet, and the mass is 0.01 pounds. We have air in this system. State two, we have atmospheric pressure, 14.7 psi, and we're told that the process from state one to two is a polytropic process where PV to the power of 1.5 is constant. We're also told that the specific gas constant for air is 53.35 feet pounds force divided by pounds mass degrees Rankine. Now the problem asks us to find the work and the heat that happened because of this process, right? And we're asked to do it with constant specific heat and with variable specific heat. So again, if we say, so we know that our system is basically what's inside our piston cylinder assembly. We know that the fluid inside of our system is a gas. And then the second part of that, what's the fluid question is it constant or variable specific heat? And we'll do it both ways today, just so you can see it, because you might get either one of these two things on the exam next week. So we start, right? Again, if you don't know what to do, start with the first law. So our first law tells us for closed systems that delta E is equal to Q minus W. We're going to make the assumption, because, in part because we weren't told any information about kinetic potential or spring energy, right? In part because for these types of processes, these types of energy changes tend to be minimal compared to delta U. So we're going to say that all those other kinds of energy changes are pretty small compared to the change in the internal energy. So then we get this version of the first law that we're starting to know and love, right? At least know that delta U, where U at the end minus U at the beginning, right? So U2 minus U1 in this case is equal to Q minus W. So this is great, we got an equation, right? But I always like to, I did this undergraduate degree that was engineering and management, right? So I like to do this accounting step whenever I have an equation, right? So here I got an equation, there's 4 terms in it, right? And unfortunately, all of these terms are unknown. So it's great that I got an equation, right? But I got one equation and 4 unknowns. And, I'm not a mathematician, but I know that that's not a great position to be in if I want to get to a numerical answer. So I got to keep going, right? So here I got 2 paths that I can pick, right? It's like a Zeppelin song. I can decide first to go for, that's a Stairway to Heaven reference. I don't know, maybe I'm dating myself. It's not even dating myself because it's older than me, right? So here we got work, right? I can take the work path first, or I can take delta U first. It doesn't really matter which one you do first. Maybe on an exam problem, just because it makes it easier to grade and it sort of helps lead you through the exam, maybe part A would be find the work and part B would be find the change in internal energy, right? But if you were just doing this by yourself, you could pick either path. You don't have to walk down the path that the problem is leading you. If you don't remember how to find work, find delta U first. Right? But in this case, I'm going to find work first. I remember that for closed systems, work is the integral of PdV between state 1 and state 2. In this case, I'm told that PV to the power of 1.5 is equal to a constant, but that by itself is not what I want, right? I want pressure as a function of volume. So I have to divide that equation by V to the 1.5 on both sides. Then I get pressure as a function of volume is equal to some constant divided by V to the power of 1.5. Now, this might just be me, but I find the calculus easier if I write this as CV to the power of negative 1.5. Right, so now I write this in my equation here. This C, I know that there's going to be some way that I can manipulate this C a little bit later. Maybe I could even find out the number now, although I'm always going to encourage you to do the problem symbolically and only put numbers in at the end, because then it's much easier for you to follow what you're doing while you're doing it. But it's also easier for me to follow what you're doing when I'm grading it, right? So I know this constant is constant. The great thing about constants is I can remove them from the integral term. So now I have this c is equal to the integral of v to the power of negative 1.5 dv. I can integrate that and evaluate it at v2 and v1, right? And now I get that c times v2 to the power of negative 0.5 minus c times v1 to the power of negative 0.5 divided by negative 0.5 is equal to the work. But I don't know what c is, right? So maybe you've gone through and you've numerically figured out what c is and it has some units. But again, I'm going to encourage you to keep this symbolic, right? So I know from the problem, it told me that PV to the 1.5 is constant. So anywhere in my process, this is true. That includes the endpoints of my process. So P1V1 to the 1.5 is equal to P2V2 to the 1.5. And both of those things are equal to C. So now C has two different possible expressions. So I'm going to try to group these things by their subscript. So I'm going to say P2V2 to the 1.5 times V2 to the negative 0.5 minus P1V1 to the 1.5 times V1 to the 1.5 divided by negative 0.5 is equal to work. And the reason that I do this is because then when we multiply V2 to the 1.5 times V2 to the negative 0.5, we just add up the exponents, right? And those exponents, when you add them up, will always equal 1. So what we're going to get here is P2V2 minus P1V1 divided by negative 0.5 is equal to the work. So now I have a numerical expression or an analytical expression for work, right? So this is good. Again, I can look at the accounting here. I know that I have the pressure at state 2. I don't have V at state 2. I do have P1 at state 1, and I have V1 as well. So now how do I find V2? So I can use, again, the fact that P1V1 to the 1.5 is equal to a constant, which is also equal to P2V2 to the 1.5. I don't know what the numerical value of C is, but I also don't really care because what I'm actually trying to find here is V2. So because both of these two terms are equal, I can equate them without ever finding C. And then I can write an expression for V2. So here I can isolate V2 and see that it's P1 divided by P2 multiplied by V1 to the 1.5 all to the power of 1 over 1.5. The cool thing about trying to group terms like this, so I have a ratio of pressures, as long as these are both absolute pressures, where the 0 is not atmospheric pressure, but a vacuum, then the units don't matter. It doesn't matter if this is in megapascals or pounds per square inch. As long as they're both absolute pressures, then I just take the ratio, right? As long as the units are the same. It doesn't matter because they'll drop out when I start to look at the units, right? So here I put all this together and I see that my volume V2 is 0.3 cubic feet. So now I know V2, right? I can put this in to my equation for work. Now I know everything. But when I do my calculations, I always have to think about the units, right? This is true in metric problems, and it's like double true for imperial units. Because the imperial units are always a pain in imperial units, right? Because you have things that are in like base 12 and other things are in base 16 and other, like it doesn't make any sense, right? So here I notice that if I just multiplied these two terms together, which I might do if I wasn't tracking my units would then be pounds force feet cubed divided by inches squared. And that unit, well, it is an energy, it doesn't really help me, right? So now what I'm going to do is I'm going to turn I'm going to try to get foot-pounds force on the top here, right? So I got to get rid of this inches squared. So I know that there's 12 inches in a foot or 12 square inches in a square foot, right? This is true for both of my terms here. So I do that math, I put some stuff into my calculator, and now I get an answer of work in foot-pounds, right? Now, you might then have to convert something to BTU, right? Which has another weird conversion factor that's 700 and something to get to foot-pounds, right? But for right now, we'll leave this in foot-pounds and see where we go, right? So this means, right, so we got a positive value here, right? So I know work in is negative, so this must be work out. This is my system pushing out on the surroundings, so the volume should be increasing, which is what I see. I started with 0.1 cubic feet, and I ended with 0.3 cubic feet, so this is expansion. This is the system pushing out on the surroundings. So it does make sense here, at least given the numbers that I calculated so far. So now this is good. If I look at my first law, I still don't know U2, I still don't know U1, I still don't know Q, but I do know work, right? I used to not know 4 of these things, and now only 3 of these things I don't know, right? So we're making progress. Next, we're going to try to find delta U, right? So the problem asks us to do this in 2 different ways, right? For the work, it doesn't matter if I'm using constant or variable specific heat, because specific heat wasn't at all involved in my calculations. Delta U, it does matter. So first I'm going to go through the whole problem looking at constant specific heats. When we have constant specific heats, that means that the change in the specific internal energy is going to be equal to CV times delta T. I'm never going to find the individual specific internal energies here, but that's okay, because the first law doesn't require that I know U2 or U1. It requires that I know the difference between U2 and U1. So here, I know that delta U is the mass, which I know, CV times T2, which I don't know, minus T1, which I also don't know, but I do know CV, so I don't know. Again, I'm left with an equation where I don't know some stuff, right? So now I have to leverage the fact that this is an ideal gas law problem, right? That means that I can use ideal gases, right? I can use the ideal gas law, and I'm going to use it in a couple of different ways here, right? So first, I'm going to look at state 1. At state 1, P1 V1 is equal to M times R times T1. I'm trying to find T1, right? T1 is going to be P1 V1 over MR. I know all of these things, right? Again, I got to watch out for units here because my pressure is in pounds force per inch squared, PSI. My volume is in cubic feet. So I still got to convert over here so things drop out correctly, right? I can check my units for R. Again, there's pounds mass in here and not pounds mole. So I know that this is the specific gas constant and not the universal gas constant. So here I look at this, right? And I see that all the units drop out except here all the units in the numerator drop out and everything in the denominator drops out except I would have 1 over Rankine. That's what the big R is. That's like Kelvin, but in imperial, right? So I'd have 1 over R, right? So I invert that fraction in the denominator and I get that this is 866 degrees Rankine. So that's good. Now I know T1, but how do I find T2? I might be able to go through and do the same thing with the ideal gas law at state 2, but honestly, I hate tracking units. Well, I don't hate tracking units. It's nice because it almost lets me cheat, right? It lets me see if my answer is correct, but it's pretty cumbersome. So when I go between state 1 and state 2, I'm also going to leverage, so I'm going to leverage the idea that this is an ideal gas law problem, so I can use the ideal gas law. I know that it's a closed system, so the mass remains constant. I also know that that we have a specific gas constant here, R, right? And actually, right, so M and R remain constant throughout the whole problem because there's no, we're not saying there's any kind of chemical reaction, that it's only air that's in our system. So the specific gas constant is specific to air, so it doesn't change. If that's true, P1 V1 over T1 is equal to P2 V2 over T2. Again, I can isolate for T2. And I like to arrange this so that I have a fraction for my pressures and a fraction for my volumes. So that if I'm using the same unit for both of those two things, I don't have to track the units as much because it's going to drop out, right? So this is going to be cubic feet divided by cubic feet, and PSI divided by PSI. So both of those things drop out. So I have 866 multiplied by two fractions that have no units. And in this case, I get that the pressure or the temperature decreases from 866 degrees Rankine to 477 degrees Rankine. So now I know T2. So this is good because now I know all the information that I need to find delta U. So delta U is equal to mCV times delta T. I know all of this. I put it into my calculator and I see that delta U is 517 foot-pounds, but it's negative, right? So heat in is positive. So this must mean that heat is leaving my system because I'm getting a negative, right? I do see that my temperature went down, so maybe this makes sense, right? So now I know work, I know delta U. Oh, yep, Jack, you got a question?
I just have a quick question. How is CV found?
So CV would be typically given on a test, or there's a table. It might be even table 1 in the textbook where you could look it up. But okay. I'll give you probably on a test I'll give you CP and CV and let you demonstrate that you understand which one to pick.
All right, thank you.
You're welcome. So now we know delta U, we know work, right? So we came from a place where we didn't know anything, and now we just don't know heat. So we got one equation and one unknown. So we can isolate for Q. Right now we know all this stuff. I checked my units here, right? Because this 517 was also in foot-pounds. So everything here is in foot-pounds. This makes sense. I'm adding apples to apples, right? And I get that in this case, it actually turns out to be that the heat is 517 foot-pounds. So now I've finished the problem with constant specific heat, right? So this makes sense. The units made sense. We get a unit of energy for all of this. For work, we got a unit of energy. For delta U, we got a unit of energy. For Q, we got a unit of energy. The signs seem to make sense, particularly for work. It's sometimes a little bit difficult to understand if U should be positive or negative, right? But in this case, the signs seem reasonable. So we got an answer, right? We can't prove that it's wrong, which is usually pretty good, right? So what would have happened if instead of branching off to this idea that we were using constant specific heats, if we used variable specific heats, right? The first part of this problem to find work would not have changed at all. So then we would have been back at this point where we don't know delta U, we don't know Q, but we do know work, right? So now we're going to say, okay, it's variable specific heat. We're going to assume, which is actually true, that the specific heats change with temperature. So this is a more accurate way of doing it. But because it changes with temperature, we can't use CV times delta T because we'd have to integrate. We can't move that CV out of our integral, right? So we can look up values on table A22, which is for air, right? So now I got to make myself a state table, which I probably should have done in the first part too, right? So the ideal gas law stuff that I did to find the temperatures, I can do that too. None of that depended on having a constant specific heat. So everything else here, finding the volume and the temperatures, that all works, right? It's just now when we're using variable specific heat, we have a different way of finding the specific internal energy. And that way is by looking at table A22. In this case, it's table A22E, right? Because we're using the imperial system, which is from the English. So I guess that's why they put an E at the end of the table here. Right, so again, we can blame the English, right, or the British for this system, right? So here, right, the nice thing about ideal gas is when we're dealing with A22, because it's an ideal gas, usually we need two independent intensive properties to fix the state. Because it's an ideal gas and we have this PVT relationship, we're okay as long as we have one of the properties that are on this table. For now, what that means for us is temperature and U, right? Specific internal energy, or maybe H if for some reason it gave that to us. Later, we'll learn how to use PR and VR, but that's like when we start to deal with internal combustion engines in like the third part of the class. So for here, right, we know the temperature is 866 degrees. So I can interpolate on this table between 860 and 880 degrees, right? So in this case, I get 6 divided by 20, or 0.3. I put that into my equation for linear interpolation, where here I'm taking the minimum value, 147.5, plus my interpolation factor, multiplied by the difference in these two numbers. You can't see it because I've clipped it out here, but on this table, if we're reading values off for specific internal energy, it's in BTU per pound mass. Now, when I tell you that, well, maybe you think that's a problem and maybe you don't, right? But we'll see that that's going to make our lives a little bit harder down the road. But the good news is, here, we actually get a value for the specific internal energy at state 1, right? Now, this is in BTU per pound mass, right? So, unlike when we do constant specific heats, all you need to know is the temperature, right? Because it's CV times delta T. Here, you need the temperature or some other property to find the specific internal energy. But we are, if we're using variable specific heats, we're going to find the actual values for U1 and U2, right? So in this case, U1 is just under 150 BTU per pound mass. State 2, again, we know the temperature is 477 degrees. So I'm going to look here, right, between 860 and 880. I'm going to find another interpolation factor, B, and that's 0.85, right? We're most of the way to 480. If I was really running out of time on a test, I would say, look, Dr. Schertzer, I don't have time to interpolate over here. I'm just going to pick 480, and I recognize that that reduces my accuracy, right? But if you write that, then that shows that you understand that you're not just randomly picking something off the table. You know, you're accepting that you're lowering your accuracy, right? So that's better than just picking something off and making me guess why you did that. Again, I interpolate, and I find here that U is 82.37 kilo. No, this should be in BTU per pound mass. This something changed on our table, right? So I guess the good news is here, before we saw that delta U was negative, right? So U2 minus U1, when we used constant specific heats, was negative, right? Because the temperature is decreasing. And we see the same thing here, right? The problem is that the units are weird, right? So here, again, I can put all this stuff into the first law, right? So I get M times the change in specific internal energy is equal to Q minus W. I have an expression for Q, right? So now I'm going to start putting stuff in, right? And I see that I get this, you know, I got to take M times delta little u, right? But here, what I'm going to find is that, you know, this is nice, right? Pounds mass times BTU per pound mass. I get something in BTU over here. But when I found work, because I was integrating PDV, I got foot pounds. This is a problem. And I wouldn't have seen that this was a problem if I wasn't tracking my units in my calculation. That is a thing that you must do, right? Otherwise, you're going to make significant errors, right? Because here, you might think that this delta U term is insignificant, right? Because it's 0.66, and this is over 1,000, right? But before, we saw that these terms, you know, that, I don't know if you remember, but the delta U term was about half of the work term, right? So if you weren't tracking units, you might not see this, right? If you were going quickly. So we need to convert BTU to foot pounds. Now, this is really interesting, and you may not have done this yet, right? So first, it's interesting that the conversion factor is some weird number like 778, right? If you're like me, you're probably not going to have memorized that, at least not yet. You might involuntarily memorize that by the end of this class, because we have to make some weird unit conversions in this class over and over and over again. But on the website, there is a sheet that's the equation sheet that you get in the exams. I think, as you're doing your homework, that it's a good idea to use that equation sheet so that you know where certain things are, right? And one of the things that's on that table, one section of that table or that sheet, is conversion factors, right? So you don't have to memorize that this is 778 foot-pounds per BTU. It's just on the sheet, right? So now if we see this, this isn't really negative 0.66. It's negative 0.66 times 778 when we put it into foot-pounds. So here I get, again, this looks like about half, right? And I find that Q is 518.7 foot-pounds. In this case, this was pretty similar. I think before, It's something like 514 when we did it with constant specific heat. So it's pretty close. And we get answers that are pretty close as long as our delta t's are small. But it's important to remember that this answer with variable specific heat, when we're looking things up on the table, is more accurate. So if we had a very large change in temperature, on the order of thousands of degrees, then our answer would get less and less accurate if we use constant specific heat. So hopefully that's both a good review of what we need to learn for the exam, but also kind of a nice look at how to do first law type problems when you use ideal gases, whether or not you have to use constant or variable specific heat. So that's all that I had to go over today. I'm happy to field any questions you may have about either this example or about the midterm in general. All right. Well, thank you for joining me again, and I will see you soon. Oh, Jack, looks like maybe you got a question?
Yeah, I just have a quick question. So, if on the exam we do have some weird conversion we have to do, what would you recommend for us?
I don't understand. Conversions you'll need to do on the exam will involve conversion factors that are provided on that equation sheet.
On the sheet?
Yes.
Okay, got it.
So you won't have to. If we were doing this in real life, like in the physical space, then usually what we would do is the department has a bunch of spiral bound, notebooks that are all the tables that are in the textbook.
Mm-hmm.
I will probably provide. I have a PDF of tables in the textbook that I will provide at the time of the exam. But I think that's more for demonstrating that you know how to look up properties. I think it's not super valuable for you to be looking up those conversions like in a textbook. So I want you to be able to show that you know how to do unit conversion. I'm not super interested in knowing that you've memorized certain values. So those conversion factors will be made available. If they're not on the equation sheet, it'll be in the question. Just a good question. All right. Well, thanks everybody for joining me.